Okay, I'd like now to talk about some single order reactions, and what we're looking at here are reactions where we start with the single reactant and we go to a product. So A going to products here, and the possible orders we're looking at would be n equals 0, 1 or 2, so rate equals k, A to be n, n equals 0, 1 or 2, rarely 3 or more, and I'll explain why 3 or more is pretty rare later on when we get into mechanisms. So if we take this and we convert this into a derivative type equation, realizing that the d here is similar to change or delta, and so the rate is going to be the change in concentration over the change in time in each case. And what we're doing is we're substituting the value of n for 0, 1 and 2. We end up with these derivative type equations. And since they're derivative type equations, they can be integrated. Now I'm not going to go into how the integration occurs or what we do, but we can find out that the integrated rate laws will all have a form of y equals mx plus b, which is a straight line. So if we start out with rate equals ka to the 0, we integrate it. This is the integrated rate law we come up with. And we've got a, which is going to be y in this case. And then we've got m, which is going to be negative k. And then we've got t, which is x. And we've got A0, which is B. Now A0 is the initial concentration of reactants. So the reactant of reactant concentration at time equals 0. So that's what we've got there. So this is going to be a constant value here. So y equals mx plus b. So y is a and x is t. Here y is log of a, x is t. Here y is 1 over a and x is t. So if we do a graph of each of these and it turns out to be a straight line, that is what the order of the reaction will end up being. This will become a lot more clear when we actually do an example, but for now just realize that we have to do this integration. We have to get this this equation that's in the form of y equals mx plus b. The other thing that's going to be important here is half-life, and we'll be doing half-life calculations, and half-life is defined as the time it takes so that half of the original amount of the reactant remains. And that means that what we can do is we can take our equation, that means any of these equations here, and we can plug in t for t equals half-life, and then we can plug in a for a0 over 2. And I'm actually going to show you an example of that. And it's going to be different for each one we do, but I'm just going to do the zero order over here. So there we go. There's our zero order. There's our zero order reaction, the integrated rate equation, and I'm going to substitute half-life in for time, and a0 over 2 will be our initial concentration over 2. That will be the amount of a remaining at the half-life. So I'll just substitute that value in. So it'll be a0 over 2 equals kt plus a0. Now what I'm going to do is I'm going to isolate, well, t half here. Now I'm going to isolate everything, and it would be kt half equals a0 minus a0 over 2. So t half will equal a0 over 2k. So there's our half-life equation. We can get the half-life equations for any of those rate equations by using a similar method to what I just used here. Alright, so let's continue on here, and we will look at some examples of zero, first and second order reactions, give you a little bit of context for what we're talking about. So if you look at a zero order reaction, the n value is 0, so rate equals, if it was in this case, it would be rate equals k n204 to the power of 0. So effectively what happens is rate just equals k. Anything to the power of 0 is equal to 1. So what this means is that the rate does not depend at all on the concentration of the reactant. I don't see the reactant anywhere in the rate equation, do you? That's not there. So all the rate depends on is the rate constant. And an example of this would be this reaction here, where we've got N2O4 reacting over a platinum catalyst to give N2 and O2. This is a similar process to what occurs in your catalytic converters in your cars. Alright, so let's look at an example of that sort of drawn out. Alright, so what we're going to do is I'm going to draw the platinum catalyst here. And the important thing to note about the platinum catalyst is that since it's a surface, the reaction can only occur at the surface, and there are only limited spaces for the reaction to occur. It's sort of like cars and parking spaces, if you like. So what's going to happen is we're going to have N2O4 floating around. We'll also have N2O4 attached to the surface of the platinum. And what's going to happen is the N2O4 will naturally take every space it can on the surface of the platinum. And then there's going to be a bunch of N2O4 floating around as well. And the point is that it doesn't matter how much N2O4 is floating around here. We can have 10, we can have 100, we can have 1,000,000. It's not going to matter. What's going to determine the speed of this reaction is how quickly the N2O4 can attach to the platinum and how quickly it can leave. Then the concentration of N2O4 on the outside is not going to affect the rate of the reaction at all. Like I said, it's just the speed of N2O4 adding to the platinum and then departing the platinum, and that's the only thing that matters. So that's what I mean when I go back over here and I say that the rate does not depend on the concentration of the N2O4. So this is the classic example of a zero-order process. And as I said before, we can calculate the half-life, and we did that by substituting A0 over 2 for the concentration of A, and T for T equals T half, and we get the half-life calculation right there. And just a point here, the half-life does depend on the concentration of the initial concentration of the reactant. Here's an example of a first-order process, and that's a radioactive decay. And the rate of radioactive decay does, in this case, depend upon the concentration of the reactant. So we're going to get more radioactive decay depending upon the amount of radioactive substance we have. And that makes sense. We know that a kilogram of uranium-238 is going to be more radioactive than a gram of uranium-238. And we know that from real life. We know that the amount of radioactive substance we have does matter for the amount of radiation that we're going to experience. So this is, like I said, a first-order process. So the amount of the rate does depend on the amount of U-238 we have. But when we go and take a look at the half-life, we can see that we substitute the values in, and what happens is A0 disappears, the initial concentration disappears. So the half-life in a first-order process does not depend upon the amount of reactant we initially start with. It actually is not part of the equation. So when you talk about half-life of any radioactive substance, you don't have to talk about the amount you initially have. It's always going to take the same time to get to half the amount you originally had. So it doesn't matter for uranium-238 if you've got a kilogram or 10 kilograms, it's going to take the same amount to get to half of what you originally started with. So that's the half-life equation there. It's going to be natural log of 2 divided by K. And here's an example of a second-order reaction. We got two NO2s becoming N2O4, and the rate equals K NO2 squared. And what's happening here is that the rate depends on the concentration of both of these because they're both involved in forming the N2O4. And that's the rationale behind that. You can see that the rate is going to depend on both of them. And the half-life equation, again, we substitute in the A0 over 2 for the A, and T equals T a half. And that's what we get for the half-life. 1 equals 1 over A0 to the K, 1 over A0 times K. And you can again see that the half-life will depend on the initial concentration of reactant, unlike in the first order process where it did not. Alright, so that gives you a little bit of background as to what some first and second order reactions look like.